I am Giuseppe Nenna and I come from ENEA, in particular from the laboratory on nanomaterials and devices. Here I will deal about organic materials for flexible electronics through impedance measurements also and to highlight the device limits. I will show in this presentation something that will highlight how there is the passage of the charges through the semiconductors, in particular based on organic materials, and then also some techniques to explore how we can investigate the transport mechanisms and the failures of this kind of devices. Organic flexible materials are important, of course, for flexible electronics, and with this kind of materials, we now are able to realize that a lot of materials, the devices that are almost similar to what we already realized with inorganic ones, but of course now they can be done on flexible substrates. And so they have other specific elements that could be useful for different applications, for example, medicines or displays and so on, but also for solar cells, as is possible to see here. And we can say also that because also the mobility of charges in this kind of materials start to become higher, also the TFTs from organic devices start to become important to develop even more complicated the devices like displays and so on. The important of this kind of devices based on organic materials is to balance, of course, the charges. Every time we speak about electronics, we have almost the same problems, and also in organic-based devices, we have this kind of problems. And in particular, we have to balance a lot of things to improve the efficiency of this kind of device. For example, if we speak about OPVs or OLEDs, we have to take care also about the coupling factor. Now, if we would like to uncouple light or upcouple light from the substrate, there is a balance factor related to charges and also the probability to have current from the pairs for OPVs or the emissive species for LEDs. And then the quantum efficiency of the materials that make this kind of devices. It's important also to say that, for example, in LEDs, is important also the fact that sometimes we lose the efficiency because we don't have emission from the triplet, not only by singlet, for example. And there are a lot of things that we have to care, but important, most important things also that we can balance in such a way, also realizing the appropriate thickness of the devices and also take care to the contacts of the device that we would like to use, is the part related to the balance of the injection of the charges. And for example, if we have a P junction with too small thickness, we will have we don't have the possibility to have a combination inside the materials, and so the whole doesn't have the possibility to recombine, and also if the mobility is too much high respect to the thickness that we would like to adopt, it will happen that the whole will go too fast, and also for the electron it will be the same, and so we will have an unbalanced structure with no recombination, and both the charges could escape without, for example, to have the emission for LEDs, no, for example. Instead, if we have I don't know, partial recombination, we can start to have this kind of situation in which we have partial recombination because of the holes, but parts of them will go through, and also for the electron the same, or we can lose part of them both. Instead, at the end of this pyramid, we can find the balance of the recombination that we would like to achieve, and to improve the efficiency of electron hole pairs, so, and control in an efficient way the charge inside the devices. Of course, as I said before, also other aspects will be important for this kind of devices, but for the moment we will see only something about the transport part. In particular today, I will speak about something that it starts to some mechanism that probably you already know from inorganic materials. For example, the metal semiconductor junction, in this case, organic junction. And there is, I will speak about a little bit about the transport inside this kind of materials, transport mechanism. And I will say something to you to help to have an understanding about what are the differences between organic devices and inorganic ones. Then I will show something about limits of this kind of devices, in particular something related to the moisture or temperature effects on this kind of devices, and then some analysis that could be useful to know to investigate the failure, in particular related to temperature effects, and then the conclusions in which we will summarize another time everything. In particular, for metal semiconductor junction, we have to say that, of course, there are some barriers that we have to take care of in this case, because as you know, the semiconductor have two barriers. One is the valence barriers, and another is conductive ones. That and to permit to the charge to be conducted inside the materials, we have to pass this kind of barrier. And when we put a metal close to the semiconductor, it will happen almost everything, because, and especially for organic semiconductor, I will show you a lot of things very important that could happen. In particular, if we are in, we don't care to this kind of effects at this moment, and we put only the Fermi level of metals close to the semiconductor, we will have two barriers. One linked to the valence band that is important for the whole charges, another instead related to electron charges. This is the conductive band. And so we can say that this is the true barrier that we have to take care to our semiconductor for N-type, as I say now, and instead this one is the one related to N to P-type. In particular, for organic semiconductor, the energy gap is depends on the lowest unoccupied molecular orbital and the highest one. And this gap is important to, for example, for LEDs to have the spectral light that it is emitted, or in particular the energy that the solar cell has to be kept from the light to conduct the charge. This kind of levels are affected, of course, also from temperature. In fact, if we change a little bit temperature, and passing from the absolute to zero, we have some charges that are able to pass from the valence band to the conduction band. And if we increase even more the temperature, it will the probability is even higher. As I said before, when we put together a metal with a semiconductor, something will change. In particular, respect to what I said, it happened that if the Fermi level will be the same, and it happened the barrier that I already highlighted before is already present, and we have also built-in potential that we have to take care. That is the one that is related to conductive barrier level. If instead we go forward in the bias and apply bias from the electrode to the other one, that now is not possible to see, but if we have this forward bias, we will give a little bit of different potential, so to the charge, in particular in this case to the electron, and so we reduce the barrier, and so we have much more possibility for the electron to pass through this barrier. Instead, if we reverse the bias, of course, it is much higher for the electron, because we have to pass a very big barrier now that we have to add also the bias that we are applying. Instead, for the holes, is even easier to pass through the barrier. But it is not so simple what it happens when you evaporate something or sputtering something, some metals on the surface of the material, and especially for organic materials, it happen that there are a lot of possibility that could happen, and in particular there are charge formations because the presence of the organic molecules, and so the possibility for different charge formation like cations or anions formation, some dipoles, or a surface arrangement of the charges with the presence of all these kind of mechanisms, or some chemical interaction with another dipole formation on interface states in the middle of the organic materials and the metal surface, or permanent dipoles. When permanent dipoles is formed, the device, of course, is almost impossible, but also with chemical interaction with the last three possibility, we have some permanent charge, and at the end we don't have the possibility to remove them also with applying voltage, and we have some memory effects also in the device, and sometimes it is possible to increase this kind of effects. For example, if you put some nanomaterials inside your organic compounds, in particular, if nanoparticles that you use are very close, for example, to the ball radius, it starts to become very important, the surface of the nanoparticle respect to the volume, and so this kind of effects are more evident, start to become predominant, and so, for example, to realize some memories with organic materials, instead to put powders with micrometers diameters is much more important to use nanometer diameters, and is important also to take care to their distribution, or for this to prevent agglomeration to use the maximum surface that is possible to use. In that case, you will have the possibility to have some dipoles around the shell or nanoparticle, and in particular, you can have the possibility to charge them, discharge, and also using different bias to read also the what you've written using the bias. So it's very easy to have this kind of effects in organic devices, and is also possible to realize easily also some memory, as we already saw in the first slide. Here I would like to say something about the transport mechanism of this kind of materials. In particular, if we would like to realize a sort of diodes, here is not possible to say, as in organic materials, that it will go in exponential way and with the exponent the voltages that we would like to apply. In fact, there are a lot of mechanisms. Okay, we have, as for them, also an ohmic transport in the beginning. But after this, it happened that the traps inside the materials, the defects of the organic materials that are much more than in an organic one, are fundamental for the transport. And it happened that it start to yes, there are other levels that we have to take care, and they depends on how are distributed the traps. In fact, it happened that the exponential the behavior is depending on the voltage, but not at exponential, and the exponential is due by the way in which the traps are distributed. And of course, the Fermi, the conductive level is not even the one that we take in mind at the beginning when we use that materials, but is a little bit lower because there are a lot of possible ways in which the charge can pass, and then start to be trapped. And when they start to be trapped in these defects, it happens that they became a sort of barrier for the others, and so they limited the other ones. And so we have this kind of a transport mechanism that is called trapped charge limited conduction. After this part, we have another kind, the possibility to have a specific law for this kind of mechanism, transport mechanism, that is called space charge limited current, that is related to the to voltage, yes, another time, but the power now is 2. This kind of mechanism is very important for organic materials, in particular for small molecules. And for this kind of materials, we have to say that the trap are much more evident too, and so we have to take care also to the trap limited charge injection, and the appearance of these levels, as I said before, it will depend on the distribution, and it will change through the Lumo levels at the end that we will use, and so the space charge limited appear at the end. So the theory formulated by Rose Lambert is very important for the transport in organic materials, but we have to take care also to the effects and so the appearance of the traps. Another, after this part, I would like to explain something related to limits of this kind of devices. Another time, if we evaporate an electrode on organic materials, we have to take to the moisture and the oxygen during the operation of this device, because the temperature start to rise, and also some chemical mechanisms start to become important, and so the moisture and of course also the oxygen can penetrate inside the cathode, and starts some phenomena like delaminations, like in this case, and also the appearance of some bubbles like here. And so for dual LEDs, for example, some spots in which it's not possible to transport properly the charges, and so there are no emissions in these parts of the device. It's important to say that, of course, here is more simple to see where are the parts that device are not working, but it is the same also for OPVs, perovskite-based solar cells, but also for other kind of devices that have a metal organic junction. Another important aspect for organic materials is glass transition, of course, because we have possibility to have more than one region in which they can work, and with the different properties, in particular when the TG happens, so we can discriminate to 3 zones: one before the glass transition, another during the glass transition, another one when they became less rapid, no? And so transit through the glass phase. To make this, to investigate these limits, we can realize several experiments. And for example, here I will show you 2 of them, but only to say to you that you can investigate easily these properties that are important, and you have to take care to a lot of things, and also to show you some ways, and so you can use them in different approaches. Here, for example, with the few things, you can start to have an idea on what are the distribution of the temperature with the air camera, and you will have the multimeter to apply the voltages and read current. Of course, something in this case for LEDs to read also the light that will go through to the device, and so you will take care to the current passing through the device, the temperature of the device too, and also the light that, and so the efficiency of the device during this kind of measurements. Okay, so it's possible to obtain an optical image, a thermal image, in which it's possible to see that in the middle is more is higher temperature, because the dissipation of the metal okay is almost the same on the surface, but the dissipation is much more difficult in the middle of the device respect to the border. Here, for example, there is a possibility to see a failure of this kind of device, in which it's possible to observe a part in which temperature rises too much, and so the material start to change, and but it's not perfectly in the middle as we expected, but is more close to the electrode, that is more resistant. Because on the bottom we have the ITO that is more resistant than the aluminium in this case. And it's possible to see that here is more difficult to conduct for the device, and so a lot of lines or current pass through this border that start to appear, and also the light pass that is able to be used for the device. Here it's possible to see also that there are two mechanisms that appears. For example, in this case, we have a first failure in the electroluminescence of the device at a specific voltage, and then we have a failure of the in terms of conductance of the device. So we can observe that we are also at a higher temperature respect to the glass transition in this case, because the used materials have a glass transition around 60 degrees. In this case, we can say that there is a moment in which, with the transition of or glass transition of this specific materials, TPD, this whole transport, we have a translation or a combination zone with much more trapped charge that could rise, and so the recombination zone will change and go in a zone that is not in the middle of the device, and so there are not emissive recombination. Here is possible another time to see that the temperature at which there is the optical failure is a specific temperature that is close to the glass transition. Instead, the electrical failure happen after, and so we can monitor how it's changing the way in which the device is working, and so we can say that probably, and we can say also that in truth, if we saw to the glass transition, the lower glass transition of the materials used is also higher than the temperature at which we have the first failure, that is the optical one. This is the optical behavior. So it changed at 9.75. At 9.75, we see the temperature that is almost around 330, that is also lower than the glass transition. It seems strange, but the surface, the glass transition surface, is even lower than the back one. So it is, and important for this kind of devices is the surface, because this is the part in which we have the recombination. So for this, we have first an optical failure and then the electrical one. Here instead, it's possible to see another limit of this kind of device, because if we change the thickness, of course, also the failure will change, because also the temperature, the way in which temperature increase will change, and so if we apply less power at a more thicker device, the temperature will be dissipated less, and so we have a failure at lower power. And there is also limits at which we have a complete delamination of the electrode, and so both the failure will happen at the same time, because the field is too much, and so the device is destroyed because of the field, and not because of the temperature in this case. We can say also that we can predict a little bit also the behavior of this kind of devices, especially if they are not so much thick with a barrier law. In this case, we use the polar iodine tunneling effects, and only to monitor how this kind of barrier can change with temperature, and we can say that it's possible to see that it's possible, yes, to make this kind of prediction with the Fourier-Nordheim formula with a specific barrier term, but that is this one, and this is the field, and this is the of course the current, and so we can say that if we monitor the difference of the behavior at different temperature, we can see that we can see that it shifted, and also the barrier will change because of temperature in this case, and this is the most important difference respecting organic materials that we can model with the Fourier-Nordheim formula, and this is because it happened that some charges start to be more free with the temperature. That is possible to see it at low voltage. In fact, are less trapped because of the defects, and it appears this kind of bias at time fields, and for this reason we can see that the barrier for this kind of devices will change because of the temperature. In particular, it will decrease, and it will decrease until the start of the glass transition region. In particular, in the first zone, as we saw in the beginning, we have this kind of behavior in which the barrier will change and will go down for with the temperature. But after this, there is another zone in which there is the transition of the material, and we can estimate the two temperature in which there is the transition zone, and then there is the complete failure of the device, and the barrier have no possibility to be recognized well. In fact, if we see the temperature is almost 325, that is lower than 338 of the glass transition in this material, and we can see that is the starting point of in which it is changing over also the heat flow mechanism, and so the appearance of the glass transition region in which in the middle we have the glass transition too. And if we put specific voltages our devices, it's possible to see that it fails at temperature, and we have the optical fail with the electroluminescence that decreases much more, and the specific temperature that is another time lower the glass transition, but is the starting point of the glass transition. That is probably the starting point, the transition phase on interface of the device. And then we have the glass transition, the appearance of glass transition region. If we see the current in this now, instead we saw there is a mechanism due to the temperature. Then we have a completely different mechanism. With the appearance, we can follow in some way the way in which we have the transition of the material. Then we have the complete failure in the third zone. This can be highlighted also through impedance measurements. It's important to say that when we use impedance, we have to take care of the fact that the materials can be considered as a capacitor, because of we have different plates in our devices, especially if we take care to the electrodes, and then there is also the resistance of materials too, and so we can write something like this. If we make a Colloidal plot, we can say that if we have only the capacitance, we have only this kind of behavior, because if we take care only to the not real part of our impedance, and so if instead we have also a resistance in series, we have all the shift of this, and so we have this kind of possibility to move for the impedance. And then if instead we apply also another resistance in parallel to the capacitance, that is the way in which almost we can say it can be designed a diodes, for example. We have not only the translation because of the series resistance, but also the appearance of this cycle, because it will change not only the real part, but also the other one, and so we have this kind of mechanism that can appear. It's important to say so that if we apply a difference of potential changing in between all, it happens that at low frequency we have the possibility for the capacitors to follow the charge and discharge, and so we will see that charge pass through simpler in from this through this part. So with the resistance bulk and not the series resistance. Instead, if we go faster, the capacitance it starts to become sort of short, and so it is important only the series resistance. This is important for also for next slides. Okay, so now if we take care also to the traps and so levels that could appear if we if we analyze our samples with the frequency, it happened that in some cases, because of the deep levels, it appears some peaks, and this is important because if we have different many interfaces and different materials, it happens that it's possible if we make the same draw in conductance respect to the pulse of so the frequency, we have the appearance of different peaks on if we realize different devices with different electrodes and so on. And moreover, I have to say, if we apply also, it's not changing only the frequency, but if we change the bias of on our materials, it happens that the cycle that we have at higher or lower frequency, it became much smaller, of course, because there is a sort of bias of the charge that passed through the conductive band, and so also in this case we can monitor how change the conductance, in this case changing the frequency and the temperature too, and it was possible to see that also in this case we have a region in which there is a mechanism, another one in which we approach to the glass transition. If we pass to the glass transition, it appears that there is only the resistance due to series resistance, and in such a way the contact on the top will start to find some way also to conduct directly with the one on the bottom. It's possible to see also this kind of mechanism changing, of course, the temperature with more temperature respect to the ones that I showed before, and only the real part, if we take care only to real part of conductance, the reverse of conductance, we see that all will go to at high frequency altogether to the series resistance. We can model this. If we remove the series resistance, it happens that the conductance will be almost parallel, all the conductance, and we can model. If we can model with the universal electrical response our device, we can have the possibility to monitor the S parameter that is on the exponential of the pulse that we apply to our device, and it is possible to see another time that this exponent will change drastically, approaching to the last transition, then it will change definitively at the end. And here it's possible to, if we take care, excluding the resistance, series resistance, we have this kind of behavior, as I said before, that go every time in the same way, and for the conductance, but also the capacitance will change at different temperature. And if we make the reverse of the conductance, so we go to analyze the bulk resistance of our device and multiply with the capacitance, it happened that we have the three zones, another time highlighted. The first zone before the transition mechanism, the one into the middle that is as before due to the transition mechanism, another when the device will fail. And so, I would like to show another time only the slide that we saw before. So we did three different zones another time to remember that what are the temperature, and we have almost the same before glass transistor, before the 336, 38, and the middle, and the last part. Okay. So today we highlighted a little bit the transport mechanism of organic materials. We saw how the temperature affects this kind of materials and parameters of the device. And we saw also some experiments to highlight how to characterize the limits due to the temperature in particular in this case, and to give you some possible strategy to approach this kind of limits. And thanks for your attention, and if there are questions, I'm here.